Hi and welcome, it's 3DE4 tutorial time. This little exercise demonstrates a quite helpful tool in 3DE4, transform to poses. For this purpose we will solve two different shots covering common cases where this script is a blessing. Adjusting a solved camera path to survey and stitching two individual camera solves. Alright, let's start with the first case and have a quick look at the shot. We see a camera panning along a set filled with markers. Some of these markers were already tracked. And we also already have an adjusted lens. So, nothing's holding us back, let's calc the shot. Both deviation curve and value are really nice. Switch to 3D orientation controls to review reconstructed points and path. Great, we have a solved shot ready to be delivered. But wait, some clever people all of a sudden found survey, and of course our sweet solved shot must fit with this suddenly appearing survey. What to do now? Track everything again with features the survey provides? Not necessarily. Of course, there's lineup controls where we can alter the camera path until it fits in every frame. But obviously you wouldn't watch this tutorial if this would be the answer. The answer is script transform 3D camera object move to poses. Short transform poses. So what is it doing? This script uses one or more stored poses to transform a camera path or object point group accordingly. This simply means we just have to line up the camera in at least one frame, then store this alignment in a pose and let transform poses do the rest. So let's start. But at first, for a better demonstration, let's open a new 3DE4 main window and place both windows beside each other. Switch to 3D orientation controls and hide the frame slider. Then adjust the view a little bit. And hide the image plane. We won't need it in any way. Okay, back to poses. In the next step, we will align the camera to survey in the current frame. Start with centering the model. The camera moved in 3D space. But since the reconstructed 3D points didn't move accordingly, we see a bunch of annoying white lines pointing from the 2D markers to their respective 3D points. For a clearer view, let's hide them by simply removing the 3D points. They will be reconstructed again after camera alignment. Select Edit, Remove Point Calc Status. And voila! No more lines than those of the survey. Good. In the next step, rotate and translate the camera a bit so it fits very roughly. Then create some lineup points with the help of the extract tools to align the camera more precisely. Have a look at the scenery. We should focus on features on table and ladder. So let's start with the table. For a more detailed demonstration of these lineup points, please refer to tutorial lineup at 3DEqualizer4.com. One little tip, although basically being survey points with 3D position data extracted from survey, lineup points are not being used to calculate the camera, thus colored differently than 2D tracking points. These nice helpers simply determine camera position for this single frame. Okay, one more on the rung. Great, that should be sufficient. The scene looks pretty good. As we can see in 3D orientation controls, the camera position in this frame is far away from its original position. But this position already indicates where the camera has to be to fit with survey. So the next step is storing this alignment. We create a camera pose. Therefore, simply click on button Store Pose. That's it. The pose is now saved in the project's database and also depicted as a red colored bar in the frame slider. A quick note, these poses do not influence the calculation process, meaning they will be overwritten when calculating the scene again. But as mentioned, a pose is saved within the project's database. Thus we can recall it with button Recall Pose. Okay, the first step is done. We have a pose. Now, how do we get the rest of the camera path to be aligned as well? Finally, it's time for script transform 3D camera object move to poses. A new requester appears. Let's place it so we can see all three windows simultaneously. In the scripts window, we find a bunch of buttons and a list listing our pose in frame 1. Now we will use this pose to magically transform the entire camera path. Exciting! To do this, simply select the list entry, then button Transform. And poof, farewell to the excitement. Nothing happened. The reason this script seems useless is the altered camera path. Transform Poses needs a completely unedited path and a separate pose as a reference position for adjusting the path. Currently, the connection between the edited frame and the rest of the path is broken. The camera's original position and rotation for this frame is lost. Thus, Transform Poses has no information about how to stitch the following keyframes to the current position. Keep in mind, Transform Poses always needs an unedited path for a correct transformation. Long story cut short, we need to calc again, then run the script. So, calc all. The camera is back at its original position. Then again, select button Transform. Welcome back, excitement. The entire path was transformed according to the stored pose. Really cool. As we noticed, all reconstructed 3D points were transformed accordingly as well. In case you only like to transform the path and neglect all 3D points, Transform Poses provides such an option. Within the script, we find an option menu. Set it to Do Not Transform 3D Points. Calc all again. Then transform the path. All 3D points are staying exactly where they were. But in our case, we need correctly transformed 3D points to check the camera path and lineup. So let's undo this action by calculating the scene, selecting Transform 3D Points, and transforming again. We successfully transformed both camera path and 3D points, so have a look at the shot. The survey is quickly drifting away, further and further as the shot proceeds, but we noticed that rotation seems to be quite correct. Obviously, the scale is wrong. The camera path is simply too small compared to the size of the survey, which can be seen easily in 3D orientation controls. To fix this, we use again Transform Poses to scale the camera path using the respective text field and buttons. Let's start with scaling the path by setting a scale factor of maybe 3. Button Transform now can scale this path without an upfront calculation of the shot. Nice, the camera was scaled, and as we can see in lineup, we are on the right way. Obviously, it has to be scaled a bit larger. Slider power and buttons plus and minus enable a finer scaling. Yeah, I could reduce power a bit, then zoom in for a better view of the table corners. Some more scaling. Yeah, that looks good. Great, let's have a look at the entire shot. The scaling now suits much better than before. But as we can see having a closer look, not all lines and points of the survey are fitting perfectly. This mismatch can be caused either by the lens. It was adjusted for a survey-free solve, and its distortion parameter and focal length value may not fit perfectly in a survey shot. Or, the survey itself can be wrong at some points. This happens quite a lot and has to be considered each time survey and footage won't match 100%. In the next step, we try to reduce this error margin by adding another pose. Setting a second pose in the last frame seems plausible. Script Transform Poses then has 2 keyframes, one each at beginning and end, to transform camera path and 3D points between these. Alright, like in frame 1, let's move the existing lineup points to their respective features. This as well. Here we go, survey is now fitting for this frame. Next, store this pose. We see another red colored bar in the frame slider, and a new list entry within the script. For a better demonstration of the next step, let's add Curve Editor to the main window. Then select one of the rotation or position curves. Okay, now have a closer look at curve and path in the current frame. We see it's everything but smooth. of course caused by our editing. Obviously, that's not acceptable. We need to transform the path again so it smoothly moves towards this new camera position. Unlike the scale transformation, we have to transform the path based on a new pose. So, as we saw in the beginning, simply transforming the current path will lead to no results, since the script needs an unedited camera path. Oh, a quick note at this point. Of course, you can use each pose individually to transform camera and points without any influences of the other poses. Let's continue our work. Calc all to reset the camera path. Then, within the requester, select both poses. We notice all scale operators are now grayed out, since the scale will be defined automatically by the two poses. Okay, click on button Transform. Great, the spikes are gone. It's all smooth now. Close the editor, then zoom out to see the entire path. This path makes much more sense regarding survey size. It now moves along the entire table. Let's have a visual check in lineup. Yes, looking pretty good. To be completely sure we got a great result, let's have a closer look. Well, it's actually not bad, but it seems we could need a bit more fine-tuning by adding another pose approximately after the first third of the sequence. Again, let's use our lineup points to modify the position of the camera. Store pose, and we're done. So, for the last time in this chapter, calc all, then select all three poses, and transform. Finally, have another look at the shot. We successfully morphed our survey-free shot to survey data. That's it with part 1. We learned about the basics of script transform poses, demonstrated with a quite common case of adjusting a solved shot to survey. One advanced tip before proceeding to part 2. Additionally to adjusting to survey, transform poses can also be used to edit a path even though survey is available. Basically, this script works like an animation tool, meaning it adds an additional animation layer on top of an existing camera path. This will transform the path according to the set poses and automatically smooths out all the spikes caused by these manual edits. Welcome to part 2. In the next steps, we will focus on another real-life example: stitching two camera paths. Usually done tediously in third-party 3D software, Transform Poses allows us to do this directly in 3DE4. So, let's have a look at the shot. We notice this shot of a green screen has two different camera movements. The first movement is a nodal pan. Well, to be precise, it's a near nodal pan, as we can see by the yellow rod. The second one is a dolly towards another part of the green screen. Well, this smells like trouble, but of course we will proceed to calc the shot. There are already 2D points tracked, and lens was adjusted. By the way, the tutorial data of this exercise, all images along with the lens file of the adjusted anamorphic lens, is available for download at 3DEqualizer4.com. The link to the archive is in the description below. Okay, continue with calc all. Deviation curve and value look not so bad. So switch to 3D orientation controls. Zoom a little bit to the camera path. Okay, we quickly see this does not seem to be correct. The path of the nodal pan is a very weird camera path, far away from a camera standing still. The second part appears to be a little curved, also not correct since the camera was moved on a track, thus should be a straight line. When looking from the side, we see way too much motion in axis Y. Back to top view and have a look at the 3D points. We see they are not really reconstructed being on a flat wall like we clearly see in the footage. Well, it's all quite messy. To check the quality in lineup, let's generate locators for each 3D point. Then switch to lineup. Oh, we should scale them down a bit. So back to 3D orientation controls. Select them. And scale them down. Back to lineup. Yeah, that's better. So have a look at the shot. We see it's looking quite correct, but we've seen path and 3D points, so we know this result here is fallacious. Obviously, we need to calc each camera movement individually. After that, these two camera paths will be stitched together with script transform poses. At first, we have to find the frame of the transition between the nodal pan and dolly. Frame 110 seems right. Alright then, in tab camera, turn on frame range calculation. Then enter the chosen range of 1 to 110. The range used for calculation is now also displayed in deviation browser and frame slider. Next, since we are calculating a nodal pan, we can give 3DE4 a hint and set camera constraint to fixed camera position. To have a better view at what happens with the camera in 3D space, let's switch back to 3D orientation controls. Everything's prepared. Calc all. We see the camera moved away from its original position and also changed its orientation, along with 3D points. Let's play the sequence. But before, set the playback range to 1 to 110, so we'll only see the new calculated part during playback. Nice. The camera is rotating in a fixed position, just like we want it to be. Also, no more movements in Y direction. Okay, nodal pan accomplished. The dolly part is already waiting. For setting up the next frame range, we can use the playback range to speed up some preparations. Simply set the playback range from the last frame to 110. Then select Calc, Frame Range Calculation, Enable. Et voila! The frame range values were updated automatically. Two birds with one stone. You may have noticed that the calculation for the second camera path starts with frame 110 and not frame 111. 110 was the last frame of the nodal pan, and obviously will be overwritten in the upcoming calculation. As we learned in part 1 of this exercise, two things are necessary to transform a camera path: an unedited path and a stored pose, so transform poses has a reference position for transforming. If we would set the frame range from 111 to 230, we would have the required unedited path, but exactly. The pose isn't within the range of this path, thus has no connection with it. This makes it impossible for transform poses to use the pose for transforming the path and stitch it to the nodal pan. To cut it short, no pose, no stitching. So, before the current camera position will be overwritten, let's store a pose for this alignment. Next, remove the camera constraint. Then, calc all. Great, we got a straight linear camera path with the correct orientation. Further, all 3D points are now positioned as we'd expect them looking at the green screen wall. Okay, finally it's time for stitching. As mentioned, we are going to stitch the dolly movement to the nodal pan. For a better demonstration, let's open Curve Editor and select Curve Rotation Y. We clearly see there's a huge gap between both parts. Of course, this gap has to be eliminated. Switch to Lineup and open Script, Transform 3D Camera Object Move to Poses. Then back to Orientation Controls. Fine, our pose appears as expected in the list, so select it. Everything set, keep an eye on the curve and both camera paths. 3, 2, 1, transform. Eureka, it worked! The curve is all smooth. The camera paths seem to be merged correctly. Close the requester in Editor, then have a closer look at the new camera path. Of course, extend the playback range to the entire sequence. Great. Both parts were stitched and the nodal pan smoothly transitions into the dolly movement. Also, movements in Y direction are correct now. "3D points were transformed accordingly as well. But wait, speaking of 3D points, where are the others from the nodal pan? All those survey 3 points currently not reconstructed simply cannot be taken into account since their tracking data is outside the frame range. But don't worry, we still can get them by triangulating their position based on their 2D tracking data and camera path. At first, select them. We can easily identify the missing points by their calc status in Point Browser. All points that weren't calced don't have the label. So let's select all calced points, then simply invert the selection. Next, disable frame range calculation. Currently, all points we'd like to triangulate are outside the current set frame range. Finally, select Triangulate Points. We see all selected points are now labeled as calced. But where are they? Not here. Not here either. Ah, there they are, quite far away. Why this should be fixed is best demonstrated in lineup. Playback the shot. Unlike in the dolly part, all locators are missing in the beginning. Well, they are not missing, they are simply tiny, caused by the far distance. So how do we get these points closer to the camera to match them with those of the dolly movement? Of course, without messing them up. Quite simple, there's a script for that. Switch to 3D orientation controls. Then, with the effective points still selected, click on Push Points. A new requester appears, offering us some buttons to move points in different directions, a slider to set the push factor, and an option menu to define if the pivot for pushing is the camera position or a specific 3D point. Obviously, we need to push points towards the camera. If it would work. Nothing's buggy here. The script simply solidly works with survey points. So with all these points still selected, click Edit, Convert to Surveyed. Open again Push Points. Then try again moving them towards the camera. Nice, now it's working. Alright, seems we got the correct distance. Back to lineup. The scale of the locators is a bit too small now, so let's scale them up a bit. Select all locators, then scale them up a few times. Again, back to lineup. Looking much better. Okay, play the sequence. Perfect. Camera movement is nice and smooth, and all 3D points are now correctly placed across the entire shot. We successfully stitched 2 camera paths in 3DE4 to solve this shot. Working with this data is much easier for the artists in other departments. That's a great script, isn't it? We learned about the magnificent tool Transform Poses with the help of 2 scenarios. First, we had a perfectly solved survey free shot and had to adjust the solve to survey. For this purpose, we lined up the camera in some frames using lineup points and storing these alignments in poses. These poses were used to transform the camera path. Second, we had to solve a shot containing a nodal pan and dolly movement. Therefore, we solved both moves individually and stitched them with a script. In addition, we reconstructed all points of the scene by triangulating those outside the frame range, then pushing them to their correct positions. Well, that's it. Thank you very much for watching. I hope you enjoyed this tutorial.